All right. Hello, everyone. Thank you for staying until the last session. It's great to be here to talk. I think after this, there's a panelist, and then we'll be done for the day. It's really great to be here. I think this is my third or fourth time here, and it's been great to start to recognize more and more people as I go through. I am not Miles. I am Dan. Miles is unable to be here with us, so I got the privilege of being here to talk to you all about some of the tools that we have created. To give you a quick introduction of myself, I'm Dan Jang. I'm a PhD candidate at ArcLab at MIT, advised by Professor Richard Linares. And previous to starting my PhD program, I was actually at MIT Lincoln Lab on the SSA side and a lot of the government programs, trying to figure out what to do with all these counter space threats, and also looking at our SSA suite from Kwajalein Atoll all the way to Millstone Hill in Massachusetts, with all the radars down to the W-band, millimeter waves, and optical SSA sensors, trying to see what we can do to figure out what's happening in space better. And it's really been cool to see in the past decade, all the commercial sector coming in and problems like STM that we're all trying to solve and be a partake in. So it's really great to be here. And today I'd like to talk a little bit about some of the tools that I mentioned first in a very introductory manner last year at this conference, which is called the MOCAT, and MOCAT stands for MIT Orbital Capacity Tool. And now we have MOCAT-SSEM that we have created over the past year. We have different modules that have come out, and we have now put it all into one suite that everyone can use. It'll be open source and available. And SSEM stands for the Source Sync Evolutionary Model, and we're going to use this for space debris environmental modeling. So as we talked about today, and as we all know, space is becoming congested. We want to figure out what is going to happen into this environment and this resource that we all share. What do we do with that? And as we look into the future, into the centuries, we want to perhaps figure out what the orbital capacity is. How many things can we fit in there? And that, I think we all can understand that that's not an easy answer to just go ahead and give a number to. It really depends on so many use cases, what your risk tolerances are, how do you model certain things, and what kind of regimes are we looking at. So looking at the modeling of the LEO environment and looking at the evolution of the population, there's many things that we can consider, but there are two large ways to try to attack this problem. One, we call source sync models, or source sync evolutionary model, SSEM. And on the right, you can see the Monte Carlo methods, the MC methods. To describe the source sync model a little bit, really, we are categorizing every object that we care about into a few object species. So we can call one species payload. One could be derelict, one could be debris. And we're just tracking the number of satellites in a particular altitude shell. And you can have multiple of these shells, and all of these are governed by a set of ODEs, coupled ordinary differential equations, that describe how they interact with one another as the populations go up, how they deorbit, and other perturbations that we care about. So we'll talk a little bit more about that. And it's really a generalized model to look at this in a very simplistic way. If you remember Kessler and Kessler syndrome, that's how he looked at some of the stability points to see at what point are we going to be out of control. And this takes that, and a lot of other people have looked into this sort of particle in a box way of looking at the orbital debris, orbital numbers, and we are adding to that, and we'll show a little bit about that today. It's really quick. Low computational cost is really important if we're trying to propagate, so to speak, this into the future, centuries into the future, try to figure out how many things we can start to fit in. And with this, we can have some optimization layer on top of this to answer some interesting questions. On the other side, which we won't talk about today much, but it is the other corner of the spectrum, is the Monte Carlo methods, where we sample from random variables for the initial conditions. Individual objects have individualized orbits and physical parameters that we can track, which is not necessarily true for the source sync side. Here, really, it's a high computational cost because you're propagating perhaps millions of objects into the future, trying to see, do they collide? If they collide, what happens? And you need to have many, many samples to have some confidence of the statistics that you get at the very end. So it is a method that is more used today and a little more believable, perhaps, just because we're able to track every single object and you know what's happening to them, you know exactly what's going on. Source sync side, it is pretty generalized, but really we call both of these together, the MIT Orbital Capacity Tool, the MOCAT tool, and we're trying to bridge the gap, try to have best of both worlds of being able to do fast computation, but also something that's believable and validated. So we'll start with a description of the three model MOCAT-SSEM, which is the MOCAT-3. Here you can see P stands for the number of objects. So that's the variable that we're tracking for a particular shell. So this is the altitude shell, circular shell, that we're assuming is the objects are moving around and colliding perhaps in a particle in a box format, ideal gas. And P here with a 3, we're dividing it into payload, derelicts, and debris objects. So ST and N. And on the top, you can see what that OD looks like. The P dot, so the changes to all these variables will depend on things like launch, things like PMD or post-mission disposal. Do they fail? Then the payloads will become derelicts. F for drag, atmospheric drag, and C for collisions. So you can see how they interact here within one shell. And you can imagine you have multiple shells until you reach the end of the LEO regime that you care about. And of course, this could be extended into other orbital regimes, but the ones that we're looking at currently are the LEO satellites. So for each of these terms, what that looks like can be described here. A little more in depth, you can go into the paper to understand exactly what is happening, but to just give a quick summary, lambda gives you the launch rate. So you're really, hopefully, just launching satellite payloads. So that affects just the payload number. This is for a particular shell. Post-mission disposal, most of these, hopefully, will deorbit from post-mission disposal that goes right. And if it goes wrong, then it'll become the derelict, which is why those two terms are in there. And the drag coefficient, that will only matter for the derelict and debris objects, simply because they're the ones that are not station kept. Payloads are station kept. So we're assuming there's no drag force at play for that. Now, the last one is the big one of collision source. You can imagine all of these species will interact with one another, and how that interacts are shown here. And you can see that it's really a square term because that's the number of collisions that you'll get within a shell as the number grows. So if you have n objects, you can imagine that n squared is the scaling law for the number of collisions. So that's what's shown here. And some other shell-to-shell interaction is shown on the bottom. But really, this is the simple case for the MOCAT-3. So this is what the ordinary differential equations that are coupled look like for the 3 species model. For the fragmentation model, I'll just quickly talk about how we are implementing the NASA standard breakup model that a lot of people are using, also known as Evol4. We're currently using the collision model for this. So if you're given a characteristic length, you're able to see for a given mass, for a given delta V for collision, what kind of numbers and what kind of sizes of objects do we see. So on the right here is actually a MOCAT-MC model for the implementation that we have. We have added on some mass conservation to this and some momentum conservation, at least for the MC side. But you'll see that trying to fit this kind of information into the simplified SSEM model is not a hard and fast rule. So for example, our debris model is all characterized as 0.6 kilogram debris. How do you fit 10,000 objects, let's say, that's created from a collision into that when all these different masses are present? So that kind of problem is something that we want to solve in the past year, and what we were able to do in these many different versions that we have had. So in the past year, year and a half, as we were developing this, we started with the MOCAT-3 model, which really just looked at the payload, derelict, and debris classes. We've added on slotted constellations. I know there was some conversations earlier today about geo-slotting, but Miles has done a lot of great work into LEO slotting. So if you have questions, please go to him. But how do we deal with the slotted satellites as we have more and more mega constellations and proliferated LEO objects? And on the right, we also started looking at untracked lethal debris, also known as lethal untrackable LNTs. 4B added in rocket bodies, which makes sense as a source for a lot of these debris. Next, we looked at different binnings of masses, which is addresses the question that I had earlier of how do you model a number of objects after collision into just one bin that has one particular mass. And lastly, just earlier this year, we implemented the orbit raising of the population. And really, from all these different features, we're combining it all together and reformulating it in an object-oriented manner that's easier to use for users, for developers. That's what's described in the paper for this conference. So that's what we're calling MOCAT-SSEM. So it's no longer MOCAT- number, but we can just call all these together into one unified model called MOCAT-SSEM. So the structure is shown here. You can go deeper into it in the paper, but we have a scenario property that we define, and we look at the implementation. So how are the species defined then? So that is all automatically done once you give it to a scenario. And a big portion of what this SSEM tool gives us is the automatic building of equations. So you saw earlier that table that had a lot of different coefficients. and how do you bin those things if you have different masses? How do they all interact with one another? That really grows around n squared as well. If you have n species, they're all going to interact with one another. So there's a lot of terms to follow. Previously, we had to build that manually. So all those different versions that we saw earlier, those were all manually built. The tables were manually built, and we had to go through all of that. But now, with this SSEM structure and restructuring of this, this tool, we're able to automatically build that, which is, I guess we're calling the equation builder here in the middle. After that, we can integrate it. We could do a visualization layer that's built on top of this to understand what's happening. We'll show you some of the examples here. And then hopefully, or we have used it for optimization to answer some key questions like what are the equilibrium solutions for orbital capacity, which really requires a lot of running this tool many, many times, and which is what the Monte Carlo tool is not necessarily suited for. So that kind of questions and optimization layer is a very big portion of this tool that we're hoping to address. So here's an example model built by SSEM. Here we show you 4 different mass properties for the payload class, which means we have 4 different ones for derelict. They can become derelict depending on if you fail a KMD or not. We have the rocket body class and 3 different classes for fragments. How do they interact with one another? Again, this is just shown for one of the altitude shells, but you can have multiple altitude shells that are interacting with one another as shown here, depending on drag forces. So an example case here, if you have no future launch cases and is shown here, and you have S, they're all defined here as for slotted satellites, SU for unslotted, derelict and debris, and you can see the masses of these different ones. And when we start with the initial population and you stop launching cases, what happens? Which is an interesting case that we always look at on the MC side, and as we look at different policies, where are we in terms of the stability region? You can see satellites, because they PMD or deorbit, you can see they all go down to 0 pretty quickly. D rises, however, because although payload class will be, some of them will become derelict. So some of these failed PMDs will become derelict objects, which is why it goes up. And then you can see for the lower shells, they start to decrease a little faster, but the higher ones, of course, the drag forces aren't really in effect here, so they stick around. Rocket body, similar idea, but if you look at some of the debris classes, you'll start to see that they have a higher area to mass ratio. So for the lower classes, they deorbit a lot faster, but of course the higher ones stick around. So if you merge all these together, you can start to look at answers as this. If you have an initial population that looks like shown here for the different altitudes, how does that look like in as we go into the steady state mode? And you can see that also here. Note that this is for a density in terms of objects per kilometer squared. It's not necessarily mass or such, but if we're just looking at numbers, these are the types of plot that we can do. And you can imagine if you have different launch profiles, what does that do to this model? What kind of stability points are we able to look at? So with that, I'd like to just say that MOCAT-SSEM is this new framework that we're combining all the work that we've done in the past year and building this SSEM model. We're hoping to enhance this code reuse, make it more modular and easier to use, and adapt from all the developers and the users who are interested. And verification is ongoing, so that's the big push between the MC side and the SSEM side, trying to merge them together so that we have a better model to be able to measure and understand the debris population such that we have regulations that make sense in the future. So verification is ongoing, but if you are curious about what the state of this code base is, it will be made open source after this. So if you're curious, we are looking for either collaborators or users. If you're curious about this, please come and talk to us. We are currently talking with many other organizations who are interested in figuring out what kind of capacity are we coming up with. So we'd love to talk to you more if you are curious. With that, I'll take any questions.
Dan, what's the advantage of separating out the debris into derelict and rocket bodies and fragments as opposed to just saying it's debris?
Right. So that is a great question. At a certain point, as you do multiple mass bins, you can imagine that is just the same between derelict. It's just a big debris. But the mechanism of transfer of failed PMDs becoming this derelict object and it's staying there, that and how that interacts with the other debris objects, that's how it made sense in the very beginning. It's in some sense a legacy thing from MOCAT 3 days because we never had a debris class that was big. But now that we have mass binnings, you can start to merge these and have it a little more flexible. So that is a good point in terms of how the species can be defined. that is really a man-made definition. So that's really something that we can play around with. Okay, all right, I got the kill, so I'll talk to you Carson separately. All right, thank you so much.